Right now, something so large it barely fits inside language is already on its way. Not a comet, not an asteroid, not a rogue planet. A whole galaxy is falling toward us, carrying 1 trillion suns like glitter in a black ocean. And here is the weird part. This is a disaster you would not hear, and a collision you might not feel, even while the sky is being rewritten above your head. The universe is calm like that. It does not warn you. It just changes the rules quietly. Stay with me until the end, and if you enjoy this kind of cosmic investigation, please like and subscribe. When you hear the word collision, your brain probably pictures impact. Metal crunching, fire. A sharp moment where before and after are separated by a single violent second. A galaxy merger is the opposite of that kind of drama. It is slow motion so extreme it becomes surreal. It is a story measured in millions of years, with chapters that last longer than the entire history of our species. And yet this is not a distant abstract event happening somewhere in a random corner of the universe. This is our neighbourhood. Our Milky Way has a neighbour named Andromeda, and Andromeda is not just sitting there politely across the void. It is approaching. It has been approaching for a very long time. And the best measurements we have say that in roughly 4 billion years, give or take a few 100 million, the two will meet. That timescale does something strange to the mind. 4 billion years feels like never. But it is also a number that matches the age of Earth itself. It means the collision is not some fantasy future beyond imagination. It is the next major event in the life of our galaxy, and the galaxy does not care how we feel about it. So what does it mean exactly for a galaxy to hit another galaxy? First, we need to be clear about what Andromeda is. In the sky tonight, if you are far from city lights and you know where to look, you can see it as a faint smudge. It is easy to miss. It looks like a small fuzzy cloud with no shape, no sharp edges, nothing that screams galaxy. That is the lie distance tells. That smudge is a spiral galaxy larger than ours in diameter, filled with roughly 1 trillion stars, maybe more. It is about 2.5 million light years away, which sounds impossibly far, until you remember that on the scale of galaxies, that is basically next door. And that next door neighbour is moving toward us at a speed that is ridiculous by human standards and oddly gentle by cosmic standards. It is a little over 100 kilometers per second. That is faster than anything you will ever experience, and still slow enough that the story takes billions of years to unfold. The universe is patient. Gravity never gets tired. Gravity is the main character in this entire film. Not as a villain, not as a hero, more like a law of nature that does not negotiate. If two massive things exist in the same region of space, they pull on each other. Always. They can drift, orbit, dance or fall, but the pull is there every moment. And when you zoom out far enough, you start to see that a galaxy is not a static object at all. It is a moving pattern made of stars, gas, dust and dark matter, all of it held together by gravity like a flock of birds held together by instinct. When galaxies merge, the first instinct is to picture stars crashing into stars. That seems unavoidable. How can two swarms of hundreds of billions of stars pass through each other without a catastrophic pileup? The answer is one of the most counterintuitive facts in astronomy. Space inside a galaxy is mostly empty. Not empty like a room with nothing in it. Empty like a desert the size of an ocean, with 1 grain of sand every few football fields. The stars in a galaxy are bright, but they are also tiny compared to the distances between them. So the collision is not a crash of stars, it is a collision of structures, collision of gravitational fields, collision of orbits. If you could somehow live long enough to watch the merger from a safe seat, you would not see a sudden explosion. You would see a slow stretching, a slow twisting, and then a slow blending, as two spiral patterns are pulled apart and remade. The night sky would become an evolving mural. And what is eerie is that your daily life, on a planet like Earth, might stay almost completely normal for a long time. The sun would still rise, the seasons would still change, the danger would not feel urgent, even while the galaxy is doing something monumental around you. That is the paradox we are going to live inside for this entire story. The biggest event in our galactic future is not loud. It is not fast. It is not a punch. It is a long gravitational argument that ends with a new galaxy being born from two old ones. Tonight, We are going to walk through that argument from the first clues that Andromeda is approaching, to the first signs that the merger has begun, to the moments when the skies become crowded with new stars, and finally to the end state when the Milky Way and Andromeda are no longer separate names. Just one new system, with one shared centre, and a sky that no longer looks like home. But before we can see the collision, we need to know what is colliding. We need to get oriented inside our own galaxy. Not the romantic Milky Way band you see on a clear night, but the actual structure, the real shape, the real scale, the place where we are standing without realizing it. Because once you truly understand what the Milky Way is, you start to feel the weight of what it means for another galaxy to come rushing in. The Milky Way is the one place in the universe we talk about constantly, and also the one place we almost never picture correctly. That is not our fault. It is hard to understand the shape of a forest when you are standing between the trees. Every night, the galaxy looks like a pale river of light spilled across the sky. Beautiful, sure, but it hides what the Milky Way really is, a structured, rotating machine made of stars, gas, dust, and an enormous amount of invisible mass, all of it bound together by gravity and time. Astronomers classify the Milky Way as a barred spiral galaxy. Imagine a broad, flat disk like a cosmic vinyl record, except the record is about 100,000 light-years across. Now imagine that disk is decorated with spiral arms, long curving lanes where stars and gas tend to gather, and in the middle, instead of a simple bright dot, you have a stretched bar-shaped concentration of stars. That bar is not a decoration. It is a sign of motion and instability. Bars form because the gravity inside the disk is constantly rearranging itself, like a crowd shifting in a stadium. At the very centre of that bar, buried behind thick curtains of dust, sits Sagittarius, a star. That is the supermassive black hole at the Milky Way's core. Its mass is about 4 million times the mass of the Sun. That number sounds like an ending. 4 million suns compressed into a region smaller than our ability to picture. But the black hole is not the whole centre, it is the anchor point. Around it is a dense swarm of stars, and farther out a bulge of older stars, and beyond that the spiral disk we live inside. Now here is a quiet truth that changes the mood of the story. Even though Sagittarius' star is unimaginably massive, it is not pulling on you right now in any noticeable way. From where we are, the central black hole is far away. Gravity weakens with distance. The Milky Way is not held together by one monster at the centre. It is held together by the combined mass of everything spread out across an enormous volume. The black hole is the emblem, not the glue. So what is the glue? Some of it is visible matter. Stars, gas, dust, planets, all the familiar stuff. The Milky Way likely contains somewhere between 100 billion and 400 billion stars. That range is not because astronomers are sloppy, it is because counting stars from inside the galaxy is like trying to count every raindrop in a storm while you are standing in the rain. Dust blocks the view, distance distorts brightness, and faint stars get lost in the glare of closer ones. And even if you could count the stars, you still would not have the full mass, because the galaxy is not just a disk of visible light. It is wrapped in a much larger halo of dark matter, an invisible structure that outweighs the stars by a wide margin. You cannot see dark matter. It does not shine. It does not block light. It just sits there, quietly shaping the orbits of everything else. We will come back to that invisible scaffold later, because when Andromeda arrives, the first thing that really merges is not the glowing disks. It is those dark halos, overlapping like two enormous shadows passing through each other. For now, stay with the part we can feel in our imagination, the spiral disk. The disk is not a solid plate. It is more like a thin city made of star systems, with most of the space between them empty. The spiral arms are not rigid structures either. They are more like traffic jams of stars and gas, regions where material piles up as it moves around the galaxy. Stars pass through arms persist as patterns. The Milky Way is a story of motion that has been running for billions of years. The Sun is part of that motion. Right now, our solar system is orbiting the galactic center, and it takes roughly 225 million years to complete one loop. That single orbit is longer than the time since dinosaurs first appeared on Earth. So when you look up at the night sky, you are seeing a galaxy that feels eternal, but is actually dynamic, constantly rearranging itself, constantly changing its own internal weather. And that brings us to the question that matters for the collision. How stable is this pattern? Spiral galaxies look orderly. Arms, disk, rotation, a center. It feels like a well-built thing, but that structure depends on a delicate balance. The stars in a spiral galaxy are mostly moving in the same general plane, in broadly organized orbits. That shared order is what keeps the galaxy flat and spiraled instead of puffed up and featureless. If you disrupt that order strongly enough, the spiral shape does not survive. Andromeda is exactly that kind of disruptor. When another massive galaxy approaches, it does not need to physically hit individual stars to change everything. It only needs to tug on the overall gravitational field. Even a small change in the gravitational environment can, over millions of years, turn tidy orbits into messy ones. A slight nudge becomes a gradual drift. A gradual drift becomes a new orbit. A new orbit becomes a different galaxy. So the Milky Way we know is not a permanent home. It is a temporary arrangement of motion. It is a pattern that has lasted a long time, and it will last a while longer, but it is not immune to the pull of a neighbour the size of Andromeda. There is another reason the Milky Way is difficult to picture. We are emotionally inside it. It is our cosmic identity. The phrase our galaxy sounds like ownership, like safety, like belonging, but the truth is colder and, in a way, more beautiful. The Milky Way is not a shelter. It is a river of stars, and we are one leaf in the current. The collision will not destroy the leaf by impact. It will change the river. To understand what Andromeda will do to the Milky Way, we have to understand Andromeda itself, not as a smudge, not as a myth in the sky, but as a physical object with its own structure, its own history, and its own violent past. Because Andromeda is not arriving as a blank slate. It is arriving as a galaxy that has merged before. When you look at Andromeda from Earth, it does not look like a threat. It does not even look like a galaxy. On a dark night, far from streetlights, it appears as a faint smudge, a soft blur that feels more like an eye trick than a city of stars. That is the first psychological trap in this story. The universe hides its giants behind distance, and our brains are easily fooled by anything that refuses to have edges. But Andromeda is not a smudge. It is a spiral galaxy, similar in general shape to the Milky Way, and larger in size. Its diameter is roughly 220,000 light-years across, more than twice the width we usually give our own galaxy. It contains roughly 1 trillion stars, maybe more. When you say that out loud, it becomes hard to keep your sense of scale intact. 1 trillion stars is not a number you hold. It is a number you surrender to. If Andromeda's full extent were visible to your naked eye the way it truly is, it would not be a dot. It would be wide enough to make the moon feel small by comparison. The reason it does not look that way is simple. Most of Andromeda's light is spread thin across the sky. Only the bright central region stands out. So what we see is a concentrated glow, a small bright core with the rest fading into invisibility. It is like seeing a city at night from far above the clouds and mistaking a cluster of downtown lights for the entire place. Humans have noticed this smudge for as long as we have looked up. Long before anyone had the idea of galaxies as separate islands of stars, observers wrote about a strange cloud in the constellation we now call Andromeda. The Persian astronomer Abd al-Rahman al-Sufi described it in the year 964, calling it a small cloud. That phrase is so gentle it almost feels funny now. 1 trillion-star galaxy reduced to a cloud, just because it is far away. For centuries that is how people thought about it. A fuzzy object, a curiosity, a patch of something inside our own galaxy. And that is the second psychological trap. When you do not know the distance to something in the sky, you instinctively shrink it. Your mind pulls it inward. It becomes part of your familiar world. The shift happened in the early 20th century, when astronomers finally found a way to measure distances beyond the Milky Way with real confidence. Edwin Hubble looked at Andromeda and identified individual stars inside it. The key idea was simple but powerful. If you can find stars whose true brightness is understood, then the way they appear from Earth tells you how far away they must be. Hubble used that logic to show that Andromeda was far outside the Milky Way, not a cloud inside our galaxy, but a separate system entirely, separated from us by an ocean of intergalactic space. That moment quietly detonated the old universe. Before that, many people thought the Milky Way might be the whole cosmos, or at least most of it, a single great structure with a few odd clouds inside it. Andromeda shattered that view. It proved that the universe is filled with other galaxies, each one its own sprawling machine of stars. It took the word universe and made it larger overnight. Today we refine the distance. Andromeda sits about 2.5 million light-years away. That number is still mind-bending, but now it has a different flavour. Not mystery. Measurement. It means Andromeda is close enough by galactic standards that we can map it in detail. We can study its structure. We can trace its motion. We can see evidence of what it has been through. Because Andromeda is not a peaceful, untouched spiral drifting through time. It has a past that looks, in hindsight, like rehearsal. Astronomers see streams and shells of stars in its outer regions. These are not decorative patterns, they are leftovers. Stellar debris from smaller galaxies that wandered too close and were torn apart by tidal forces. Their stars were pulled out into long arcs and scattered into Andromeda's halo, like footprints from an old meal. In other words, Andromeda has merged before. It has swallowed neighbours before. It has grown by taking other galaxies into itself. The Milky Way has done this too, and we will talk about that later. But the point lands right here. Our approaching neighbour is not an innocent bystander. It is an experienced participant in the slow, repetitive violence of cosmic growth. So when we say Andromeda is coming, we are not just saying a galaxy is moving in our direction. We are saying a massive, structured, living pattern of gravity is approaching another massive, structured pattern of gravity. Two systems shaped by billions of years of motion, carrying their own scars, their own satellite galaxies, their own dark matter halos, their own central black holes. This is not one object hitting another object, it is two histories becoming one future. And now the question sharpens. How do we know it is actually coming toward us, and not simply drifting in a way that could still change? Because if we are going to tell the story of a collision 4 billion years in the future, we have to start with the evidence we can see right now, tonight, in the light reaching our telescopes. If you are the kind of person who does not trust big claims, you're in good company. Astronomers are professionally suspicious. So when someone says Andromeda is coming straight at us, the correct response is, prove it. Not with vibes, not with pretty pictures, with measurements that still work even if you do not believe the story. The strange thing is that the universe does give us a way to measure motion across absurd distances. We cannot watch Andromeda crawl closer night by night, because the movement is far too small for human eyes. But light carries receipts. You already know the basic idea from sound. When an ambulance drives toward you, the siren sounds higher. When it drives away, the siren drops lower. That happens because the sound waves get squeezed together when the source is moving toward you, and stretched apart when it is moving away. Light behaves the same way. Not because light is sound, but because light is also a wave, and waves keep the rules. When something in space is moving toward us, its light shifts slightly toward the blue end of the spectrum. When it is moving away, the light shifts toward the red end. This is not guesswork. It is a measurable change in the exact fingerprints inside the light itself. Here is what that means in practice. Astronomers do not just look at Andromeda and say it looks bluish today. They take Andromeda's light and split it into a spectrum, a spread of colours so fine that you can see specific patterns and dark lines. Those lines come from atoms and molecules absorbing certain wavelengths. They are like barcodes for the chemistry of stars and gas. And the key is, those barcodes should appear at very specific positions when the source is not moving relative to you, so you measure where the lines are. Then you compare them to where they should be. If the whole pattern is shifted slightly toward the blue, the source is approaching. If it is shifted toward the red, it is receding. When astronomers did this carefully for Andromeda, they found a blue shift, not a maybe, a consistent, measurable blue shift. And from that shift, they calculated a speed along our line of sight of about 110 kilometers per second, which is about 250,000 miles per hour. Fast enough to make your stomach drop, slow enough to make the collision feel like a distant rumour. At this point you might think the story's finished. We measured the approach, we know the speed, we can just divide distance by speed and get a date. Reality is not that polite, because the speed we measure from blue shift is only one part of the motion. It is the toward us or away from us component. Astronomers call that radial velocity because it is along the radius of our line of sight. But Andromeda can also be moving sideways relative to us across the plane of the sky. That displaced motion is called proper motion, and it is much harder to measure because the angle changes are tiny. This is where the uncertainty enters, and it is not an embarrassment. It is honest science. Imagine standing far away from a drifting boat at night. You can tell if it's coming toward you by how the engine sound changes, but it could also be sliding sideways, and from far enough away that sideways drift is almost invisible. If you only measure the toward you component, you might think it is aimed directly at you when it is actually going to pass a little to the side. And that difference matters. A direct hit produces one kind of merger. A near miss produces another, still a merger, but with a different first dance step. So astronomers needed to measure Andromeda's proper motion, the sideways drift. That is brutally difficult because Andromeda is so far away that even a large sideways velocity corresponds to a minuscule change in position on the sky. You are trying to watch a galaxy move the way you might try to watch a single human hair shift from across an entire continent. This is where the Hubble Space Telescope enters the story in a very literal way. It has the stability and precision to track tiny changes in position over long spans of time. By observing Andromeda repeatedly and using background objects as reference points, astronomers constrained how much sideways motion Andromeda could have. Later, the Gaia spacecraft added another layer to our ability to map motions and positions with extraordinary precision, improving the broader picture of stellar motions and the dynamics of our local neighbourhood. The result is not a single perfect number. It is a set of constraints that feed into simulations. You put in what we know about the distance, the radial approach speed, the likely sideways motion, and the mass distribution of both galaxies, including their dark matter halos. Then you let gravity run the movie forward. Those simulations converge on a rough schedule. The first major encounter begins in about 4 billion years, with a plausible window that could be earlier or later, roughly 3.5 billion years on the early end and around 5 billion years on the late end. The exact timing depends on details we are still refining, like the total mass of each galaxy, how their dark matter is distributed, and how smaller galaxies in the local group tug on the system over time. This is the part that sounds like a loophole, and it is not. Uncertainty does not mean Andromeda might secretly be leaving. The key fact remains: the light is blue shifted. The approach along our line of sight is real. The system is gravitationally bound. On the scale of the local group, gravity beats cosmic expansion. The Milky Way and Andromeda are close enough and massive enough that space stretching is not going to pull them apart. Their mutual gravity has been working on them for billions of years, and it does not stop now. So what we have is not a question of if, it is a question of how and when and what it will look like from inside. And now we can finally say the quiet sentence underneath all the spectacle. The collision is inevitable, but the merger is a process, not a moment. To really feel that, we need to confront the most counterintuitive truth of the whole event. When galaxies collide, almost nothing collides at all. Here is the fact that makes galaxy mergers feel like they belong in a dream. Two galaxies can pass through each other, and almost no stars touch. You can say that sentence 100 times and it still sounds wrong because your brain is built for crowds. When we picture a galaxy, we picture density. We picture a packed swarm. We picture a billion glittering points jammed into a disk. In our minds, it feels inevitable that a collision must mean endless impacts. But a galaxy is not a solid object. It is a pattern in space. It is a choreography of things that are individually tiny compared to the distances between them. Think about our own neighbourhood. The nearest star to the Sun is about 4 light years away. 4 light years is not a poetic phrase, it is a brutal distance. Even light, the fastest thing we know, takes 4 years to cross it. If you tried to travel that distance using the fastest spacecraft humans have ever built, it would take tens of thousands of years. That is how empty a galaxy really is. Most of what you call a galaxy is not stars, it is the space between stars. So what happens when two spiral galaxies approach? Their outer regions overlap first because galaxies do not have hard edges. They fade. The density of stars and gas gradually thins out with distance from the centre. So first contact is not a wall meeting another wall, it is two ghostly halos beginning to share the same volume. Now imagine a single star in the Milky Way meeting a single star from Andromeda. For a collision to happen, those stars would need to pass incredibly close to one another. Not close by human standards, close by stellar standards. And in a galaxy, close encounters are rare, because the targets are small and the gaps are enormous. This is where analogies help, because your intuition needs a translation. Picture two swarms of bees flying toward each other. You expect chaos, but now change the scale. Shrink every bee down until each one is the size of a grain of sand, then spread them out so the average distance between grains is the length of a football field. Two swarms like that can pass through each other, and you might not get a single collision. That is closer to the reality of a galaxy merger. Another way to say it is this: if you could shrink the sun down to the size of a peppercorn, then the nearest star would be another peppercorn several kilometers away. And most of that space between peppercorns would be nothing. Not air, not dust, just emptiness. So the galaxies do not collide like cars, they interpenetrate like mist. But now comes the twist. Even though the stars mostly do not hit, the merger is still violent. Not physically violent, gravitationally violent. Gravity does not need contact. Gravity reaches. Every star pulls on every other star all the time. In a stable spiral galaxy, those pulls average out into a kind of organized compromise. Most stars follow fairly smooth orbits around the center, mostly in the same plane, which is why the galaxy stays disc-shaped. The spiral pattern persists because the motion is coordinated. When Andromeda enters the scene, the compromise breaks. Stars in the Milky Way suddenly feel a new pull that does not point neatly toward our own center. It points off to the side toward a second massive structure. That pull is not constant across the galaxy. A star on the side of the Milky Way closer to Andromeda feels a stronger tug than a star on the far side. That difference is what creates tidal forces. It is the same basic principle that creates tides on Earth, except instead of water being lifted, it is stars and gas being stretched. So the real collision is a collision of orbits. Stars that have been circling in stable paths for billions of years begin to drift. Their orbits become more oval, their paths tilt, some are nudged inward, some are pushed outward. Over time, small changes accumulate into major rearrangements. It is like changing the slope of a river by a tiny amount and then waiting long enough for the entire delta to redraw itself. This is also why the merger takes so long, not because the galaxies are hesitant, because the interaction is spread across enormous distances and the system has to lose energy before it can settle. The galaxies swing through each other, then gravity pulls them back, then they swing through again. Each pass tears at the structure and redistributes motion. Each pass turns ordered rotation into a more chaotic mix. Over hundreds of millions of years, the graceful spirals become less like spirals and more like stirred paint. From inside the galaxy, you would not feel a jolt. You would not feel a shove. The forces that reshape the Milky Way act over millions of years. Your planet, your star, your entire solar system would still be held tightly together by the sun's gravity. The galaxy is changing, but it is changing like continents drift, not like buildings collapse. And that is why this story is eerie. The biggest transformations can be the least dramatic at human scale. If you could watch the merger from far outside, the drama would be obvious. You would see tidal tails, long streams of stars pulled out into space like ribbons. You would see the disks warp and stretch. You would see the galaxies brighten in places where gas is compressed and new stars ignite. You would see the two central regions swing past, then separate, then return again like dancers who cannot stop coming back together. But from inside, you would notice it mostly in the sky. The constellations would not hold still over long eras. The Milky Way band would change shape. Andromeda would grow larger, its structure becoming visible to the naked eye, until it dominates the heavens like a second Milky Way crossing our own. Night would become a permanent astronomy lesson. So when people say the Milky Way and Andromeda will collide, it is more accurate to say they will merge. And when you say merge, it sounds gentle, like blending two colors of paint. But do not let the softness fool you. The merger destroys the old structures. It scrambles the delicate order that makes a spiral. It turns a flat disk into a puffed three-dimensional swarm. It can fling stars far outward, or send them plunging closer to the center, or in rare cases, eject them into intergalactic space. Not because anything hits them, because gravity rearranges them. In the next part, we are going to step into the long approach itself. Not just the fact that it is coming, but what it will look like as Andromeda swells from a distant smudge into a looming presence. The moment the merger truly begins is not when the stars touch. It is when the sky starts telling you the truth. First contact sounds like a single moment, a date on a calendar, a clean line where two galaxies go from separate to touching. But galaxies do not have edges the way your mind wants them to. They are not coins sliding across a table. They are gradients. They fade outward, becoming thinner and thinner until the idea of an end stops making sense. So the merger begins in a way that is almost disappointing if you expected fireworks. The first thing that overlaps is the outskirts, sparse stars, thin gas, the farthest members of each galaxy's extended family. Long before you could honestly say the Milky Way and Andromeda are sharing the same space, their gravity has already started negotiating new rules. Imagine Andromeda in the sky, not as a smudge but as something that slowly swells over millions of years. At first it is just bigger, then you start to see hints of shape, a brighter center, a stretched glow, a fainter symmetry. Over time, the spiral arms become visible, not as a crisp photograph, but as a pale structure etched across the darkness. The galaxy becomes a landmark, a second great band of light with its own texture, its own depth, its own dark lanes of dust. And then the distortions begin. The outer regions of both galaxies start to stretch. Not because stars are colliding, but because tidal forces are pulling more strongly on one side than the other. On the side facing the approaching galaxy, stars and gas feel a stronger tug. On the far side, the tug is weaker. That difference gently elongates the whole system, like a soft but persistent hand pulling at the hem of a fabric that refuses to tear quickly. At first, these tidal effects are subtle, a slight warp, a faint extension, the kind of thing you would only notice if you had a sky map spanning thousands of generations. But gravity is patient. It does not need to be dramatic. It only needs time. Over the next few 100 million years, those subtle distortions grow into tidal tails, long streams of stars pulled outward into space. These tails can stretch for hundreds of thousands of light years, and they do not point neatly in one direction. They curve, they arc, they wind, because the galaxies are rotating as they approach. Each one is a spinning disk, and as gravity tugs on the outskirts, rotation turns stretching into spiraling ribbons. From far away, an outside observer would see two galaxies growing strangely beautiful and strangely wounded. From inside, an observer would see the night sky becoming more crowded and more complex, as if the universe is slowly layering a second painting over the first. This is the beginning of the merger. Not the moment of overlap, the moment the shapes stop being stable. Now we have to talk about the timeline, because this is where the story becomes genuinely weird. When the galaxies finally meet in a deeper sense, when their denser regions begin to pass through one another, it will not be the end of the process. It will be the start of a long dance. The first pass is not a permanent embrace. The galaxies are moving fast. They have momentum. They do not simply fall together and stick. Instead, they swing through each other. Picture two immense swarms interpenetrating, the stars passing like ghosts, while the overall gravitational fields collide and reshape the orbits of everything involved. The spiral arms do not survive contact intact. They are stretched, shredded, and scrambled. Gas clouds are tugged into new lanes. Stars that once moved in orderly, mostly circular paths begin to drift into more varied routes. After the first pass, the galaxies continue moving. They pull apart again, not because gravity stopped, but because they still have enough motion to carry them through. The system stretches out. The distance between the dense cores increases. For a time, the sky might even look less chaotic than during the first overlap, as if the universe is catching its breath. But gravity does not let them go. Over time, the pull slows their separation, turns it around and draws them back for another encounter. And then another. This is why the merger takes so long. You are not watching a crash, you are watching a settling. Two massive structures oscillating inside a shared gravitational landscape. A useful analogy is a ball dropped into a bowl. The ball rolls down one side, climbs the other, falls back, climbs again, each time losing a little energy, each time swinging a little less far until it finally settles at the bottom. The Milky Way and Andromeda do something like that. except the bowl is the combined gravity of their dark matter halos, and the ball is 2 galaxies each carrying hundreds of billions of stars. Over the full event, from first major encounter to final merging into one stable system, the process can span around 2 billion years. That is not a typo. 2 billion years of repeated passages, repeated tidal stretching, repeated reordering. During each pass, the galaxies lose energy, not because friction in the everyday sense is rubbing them like sandpaper, but because gravitational interactions redistribute motion. The dense central regions plough through a sea of stars and dark matter, pulling material along, creating wakes in the overall distribution, and those wakes tug back. The result is a gradual loss of orbital energy and angular momentum, a slow tightening of the dance. Each passage is more disruptive than the last. Not always in a simple straight line, but in a general trend. The first encounter distorts and begins the breakdown. Later encounters deepen the chaos. The original structures become harder to recognize. The clean spiral arms fade into memory. The disk puffs up. The motion becomes more random, more three-dimensional, like a calm school of fish turning into a storm. What does this mean for you standing on some world inside the Milky Way? It means the sky becomes a time machine for gravity, not because it shows the past, but because it shows process. You would see tidal bridges, faint lanes of stars stretching between the galaxies, like luminous threads pulled tight. You would see the 2 bright central regions drift relative to each other over millennia. And if you had records spanning deep time, you could watch the geometry change the way you watch a shadow move. And it also means a strange calm. For long stretches, daily life could remain unaffected. The forces shaping the galaxy act over huge distances and immense time, and they change orbits gradually. Your planet would keep its star, your star would keep its planets. The local clockwork continues, even while the larger system is being remodeled around it. That calm is not a promise of safety, it is simply the nature of scale. The truly dramatic effects of the merger do not come from stars hitting stars. They come from the way gravity herds gas, compresses it, and lights up new regions of starbirth. That is the next phase of the story, because once the galaxies begin to overlap in earnest, gas stops being a passive passenger and becomes the loudest part of the event. The long dance of first contact sets the stage. It stretches the galaxies, it shreds the spirals, it builds the tidal tails that will later become the bones of a new system, and it quietly turns 2 familiar homes into one shared arena, where creation and danger rise together. There is a moment in this story when the merger stops feeling like a prediction and starts feeling like weather. Not weather you can feel on your skin, but weather written across the sky, visible to anyone patient enough to compare one era to the next. And it begins in the simplest way possible. Andromeda gets bigger. At first, it is just an annoying truth that your descendants cannot ignore. The faint smudge your ancestors barely noticed becomes a bright, structured object with a clear center. Then the spiral arms stop being something you need a telescope to appreciate. They become visible as pale strokes, sweeping outward, with bright knots where young stars burn hot and blue. The galaxy looks alive, like a lantern made of 1 trillion candles, drifting closer one quiet year at a time. It is important to say this clearly. You would not wake up one morning and see a different universe. This is not a jump scare. The change is slow enough that a single lifetime might not notice it, especially early on. But if you could compare the sky from one century to the next, the difference would be undeniable. And if you could compare 1,000 years to the next, it would feel like watching a giant object slide across the heavens. Then the distortions become visible. The clean symmetry of both galaxies starts to fail. This is where the sky becomes a map of gravity, because the shapes you see are not decoration. They are physics drawn in starlight. The outer regions of the Milky Way and Andromeda begin to stretch, and the stretching does not happen evenly. The side of a galaxy facing its partner feels a stronger pull, and the far side feels a weaker pull. Gravity fades with distance, so even across the width of a galaxy, that difference matters. A star that is closer to the approaching galaxy is tugged harder than a star that is farther away, and that tiny imbalance, applied across hundreds of thousands of light years, becomes a force that can sculpt the whole system. This is tidal force in its most majestic form. The same basic idea that lifts oceans also stretches galaxies, but instead of a smooth bulge of water, you get long streams of stars and gas pulled outward into space. At first, those streams look like slight warps, delicate bends at the outskirts that a casual observer might miss. Then they grow. Over time, they become tidal tails, long luminous ribbons of stars peeled away from their original disks. Some of those tails stretch outward like arms reaching into the dark. Others form bridges, faint connections that seem to link the two galaxies together, as if gravity is tying them with a thread. And here is the beautiful counterintuitive detail. Those tails do not point straight at the other galaxy. They curve. They curve because galaxies are spinning. Each disk is rotating, carrying its stars around the center. And when tidal forces begin to pull material outward, that rotating motion drags the stream into an arc. It is like pulling taffy from a spinning wheel. The pull creates the extension, but rotation shapes it into a graceful bend. From inside the merger, you would see these arcs as vast curved lanes of faint light, slowly shifting position and brightness as the system evolves. The night sky during this phase would be almost painfully rich. Today, the Milky Way looks like a single band, a luminous fog of distant stars. During the approach, you would eventually see two great structures crossing the sky, one from our own galaxy and one from Andromeda, layered like translucent rivers of light. Dark dust lanes would cut through the glow, not as solid black walls but as soft silhouettes, places where starlight is blocked by cold material drifting between you and the background. And sprinkled through it all, you would begin to see pockets of intense brightness. These are not random sparkles. They are regions where gas has been disturbed, compressed and pushed towards star formation. Even before the most intense starburst phases, the merging gravitational field stirs the gas into new patterns. It squeezes some regions and stretches others. The squeezed regions become nurseries. The stretched regions become voids and filaments. The galaxy starts to look less like a neat spiral and more like a living storm. On the ground, life might still feel normal, if life still exists on any world at that time. The sky would be spectacular at night, but the days would still come and go. There would be no sudden surge of heat from Andromeda, no immediate shock to your planet's orbit. The scale mismatch protects you in a strange way. Galaxies are huge, but their changes are spread over so much space and time that local systems stay intact unless they get very unlucky. But the calm is not the point. The point is that the sky becomes a record of the merger's progress. It becomes evidence you cannot argue with. Even someone with no physics, no instruments, no history books could look up and feel that the universe is in motion. And for anyone with instruments, this would be a golden age of measurement. You could track the shape of the tidal tails and infer the gravitational forces that created them. You could map the shifting distribution of gas by the way it glows. You could watch how the patterns change and, from that, reconstruct the invisible structure guiding everything. Because in a merger, what you see is only the surface. The deeper truth is the gravitational field underneath, shaped by stars, gas, and especially dark matter. The sky is the visible tip of a much larger invisible sculpture. As Andromeda swells and the tidal features grow longer, the sense of inevitability becomes physical. The galaxies are no longer just approaching, they are interacting. They are deforming each other. The merger has started, not with a bang, but with a slow, elegant tearing at the edges, and that tearing sets the stage for the next escalation. When gravity stretches a galaxy, it does more than pull stars into new paths. It also herds gas into collisions, compressions, and shocks. And gas does not behave like stars. Gas can slam, heat, and ignite. That is when the merger becomes bright in a new way. Up to this point, the merger feels like sculpture. Gravity stretching shapes, bending orbits, drawing long tidal ribbons across the sky. Beautiful, yes, but still quiet, still ghost-like. The real fireworks of a galaxy merger come from the one ingredient that does not behave like a ghost at all. Gas. Stars mostly pass through each other because the gaps between them are enormous. Gas clouds do not get that luxury. Gas has volume, it has internal pressure, and when two vast reservoirs of gas meet, they can collide. Not like two rocks, more like two weather fronts slamming together. except the clouds are hundreds of light years wide, and the storm lasts for millions of years. When the Milky Way and Andromeda begin to overlap, their gas starts to compress. Some regions are squeezed by tidal forces, herded into denser lanes. Other regions collide more directly, cloud into cloud, producing shock waves that race through the interstellar medium. The compression does two things at once. It heats the gas, and it makes parts of it dense enough for gravity to grab hold locally. This is the doorway to a starburst. Star formation is always happening in spiral galaxies. Even today, the Milky Way is slowly turning gas into new stars. But during a merger, the pace can jump dramatically. Not by a little, by 10 times. In some cases, by 100 times. A galaxy that normally forms a few solar masses of stars per year can, during a strong starburst, form tens or even hundreds of solar masses per year. The numbers vary, the details depend on the exact geometry of the encounter and how much cold gas each galaxy carries, but the principle is consistent. Mergers concentrate gas, and concentrated gas makes stars. Here is the part that feels like creation in fast forward. A gas cloud compresses, fragments, and begins to collapse into many smaller clumps. Each clump continues to fall inward, heating as it shrinks, until the core becomes hot enough for nuclear fusion to ignite. That moment is the birth of a star. And when this happens across huge regions at once, the result is a galaxy lighting up with newborn clusters. You would not see the collapse itself with naked eyes from inside the galaxy. It is buried in dust and distance. But you would see the consequences, bright blue regions blooming across the sky, patches of intense light where young, massive stars burn hot and fierce. These stars are the showy ones, the kind that live fast and die loud. They can be tens of thousands of times more luminous than the sun. And because they are so bright, they dominate what the galaxy looks like during a starburst. They also do not last long. A massive blue star might live only a few million years before it runs out of fuel and explodes as a supernova. That is nothing on galactic time. It is a blink. So a starburst is not just a period of star birth. It is also a setup for a wave of stellar deaths. As the starburst ramps up, the rate of supernova explosions rises, and that changes the environment in two ways. First, supernovae flood the surrounding space with high-energy radiation like ultraviolet light, X-rays, and gamma rays. Second, they inject enormous energy into the gas around them, heating it and stirring it into turbulence. Supernovae carve bubbles and cavities in the interstellar medium, pushing material outward, sometimes merging into gigantic superbubbles that can span hundreds of light years. This feedback is one reason starbursts do not last forever. Star formation is not just a faucet you can turn on and leave running. The same massive stars that light up the galaxy also punch their birth clouds with radiation and stellar winds. They heat the gas, they blow it apart, and when they explode, they can make the gas too hot and too turbulent to collapse further. In a strange way, the most intense star formation carries within it the seeds of its own shutdown. If the burst is strong enough, the combined effect of many supernovae can drive a galactic wind. Gas becomes so hot and energized that it begins to flow out of their galaxy. Some of that material may eventually fall back in a slow fountain, mixing and returning over hundreds of millions of years. Some may escape for good, becoming part of intergalactic space. Either way, the merger is not only rearranging stars, it is rewriting the future fuel supply of the combined system. From inside the merger, the sky during a starburst era would feel almost unreal. Imagine a night that is not just filled with stars, but filled with glowing clouds. Vast luminous regions where new suns are forming, threaded with dark dust lanes like veins. The galaxies would look brighter overall, especially in the blue regions dominated by short-lived massive stars. The whole scene would feel like a universe that has suddenly decided to become dramatic. But drama always comes with consequences. More massive stars means more supernovae, and more supernova means a higher background level of radiation in the galaxy. A supernova only becomes dangerous to a particular world if it happens relatively nearby, and most are far away. Space is still huge. Even during a starburst, the odds of any one planetary system being hit by a truly close supernova remain low. Still, the risk increases compared to quieter times, and it increases for millions of years, not minutes. It is not a single disaster. It is a prolonged era where the dice are rolled more often. there is another subtle consequence. The starburst enriches the gas with heavy elements. Every supernova scatters elements forged inside stars, adding carbon, oxygen, silicon, iron, and more into the surrounding medium. Both galaxies have already been enriching their gas for billions of years, so the material is already capable of forming rocky planets. But a merger-driven starburst adds a fresh wave of enrichment, mixing it across a larger region and potentially seeding the next generation of stars with an even richer chemical inventory. So the merger becomes a kind of cosmic reset button. It is chaotic, it is hazardous in places, but it is also fertile. It creates new stars, new planetary systems, and new possibilities that could not have existed without the compression and mixing of gas. And all of this is happening while the stars themselves mostly do what stars always do. They follow gravity. The starburst is the bright face of that gravity, the visible signature that turns the merger from a slow distortion into an event you can feel emotionally when you look up. The galaxies are no longer just approaching and stretching, they are actively transforming, lighting up, and preparing to lose their old identities. Next, we follow what happens when those identities finally start to break at the level of orbits and structure. When the spiral order collapses into something puffed, scrambled and new. A spiral galaxy looks like a confident thing. It has a plane, it has arms, it has a center, it has a kind of organized motion that feels stable. But that organization is not guaranteed by any law of nature. It is a temporary agreement between billions of objects, each one tugging on the others, each one following a path that only stays neat because the overall gravitational field stays calm. A major merger breaks that calm. When Andromeda's gravity starts pulling on the Milky Way in earnest, the first thing it attacks is order. Not by smashing stars together, but by changing the gravitational landscape that those stars have been navigating for billions of years. A star that once traced a mostly circular path around the galactic center begins to drift. The circle stretches into an oval. The oval tilts out of the disk. The disk itself stops behaving like a thin sheet and starts behaving like a thickening swarm. This is orbital scrambling, and it is the reason spiral structure does not survive a big merger. Before the encounter, most stars in a spiral galaxy move in roughly the same plane, like cars flowing around a giant roundabout. Their motion is not perfectly tidy, but it is coordinated enough to maintain a disk. During the merger, that coordination breaks. Stars get nudged into new trajectories, and those nudges add up over millions of years. The galaxy stops being a flat city and becomes a puffed-up sphere of motion. If you want a human-scale metaphor, imagine two marching bands walking straight through each other. Before the meeting, each band has rows, rhythm, direction. After they pass through, you do not have two marching bands anymore. You have a crowd. People still exist, but the organized pattern is gone. That is what happens to the Milky Way and Andromeda as spirals. The stars do not vanish, the light does not turn off. But the tidy architecture is dismantled. The spiral arms are shredded, the disk thickens, and the final system becomes something closer to an elliptical galaxy, a rounded, more three-dimensional collection of stars with no clear spiral pattern and far less orderly rotation. Now the story gets even stranger, because not every star ends up in the same kind of place within the new galaxy. During a merger, some stars are thrown outward into the far halo. These are the outskirts of the final system, where the star density is low and the sky would look darker, with the bright central regions appearing more distant and more concentrated. Other stars end up closer to the new center, in a dense bulge where the night sky would be almost crowded with starlight, especially with old reddish stars that dominate later epochs. And then there is the most dramatic outcome, the one that feels like cosmic exile. A small fraction of stars can be ejected entirely, flung out of this merging system and sent into intergalactic space. This happens through gravitational slingshot effects during chaotic encounters, especially when dense regions swing past each other and the gravitational field changes rapidly. A star can gain enough speed to escape the combined gravity of the new galaxy and become a wanderer between galaxies, carrying any planets it might have along for the ride. If that happens, the experience from the perspective of a planet is chilling. Your star still shines, your days still happen, your local sky still has a sun, but the grand background of a galaxy falls away. The thick band of starlight is gone. Most of the familiar constellations fade because the nearest bright stars are now far behind you. The new merged galaxy becomes a distant smudge, slowly shrinking over millions of years as you drift farther into the void. This fate is not the most likely for the Sun, but it is not impossible. The merger turns the galaxy into a machine that can sometimes throw objects outward. Most stars remain bound, some do not. The difference is a roll of gravitational dice played over long eras. Even if the Sun stays bound, the merger can still move it. Our current orbit around the Milky Way's centre is relatively calm and relatively circular compared to the chaos nearer the core. During the merger, that calm can be disturbed. The Sun's path could become more elliptical. It could be lifted out of the galactic plane. It could end up farther from the centre than it is today, or somewhat closer depending on the details of the encounter. From a storytelling perspective, that sounds like a huge threat. From a physics perspective, it is more like a relocation within a vast city. The solar system is held together tightly by the Sun's gravity. Planetary orbits are stubborn. The merger mainly changes where the whole solar system goes as a unit within the larger galaxy. The deeper transformation is psychological. Our galaxy stops being the Milky Way in any meaningful visual sense. There is no longer a thin disk with spiral arms for you to live inside. The sky no longer has a single bright band that gives the Milky Way its name. Instead, the final galaxy is more like a glowing sphere around you, with star density depending on where you are. Near the centre it is crowded, far out it is sparse. But the familiar flat river of light is gone, and there is another ingredient in this reshaping that people often miss. While stars pass through each other, gas does not. Gas collides, compresses, heats, and forms stars, and much of it gets used up or blown out during the starburst phases. That means the final galaxy tends to have less cold gas left to form new spiral arms again. Even if the stars could reorganize, the fuel for rebuilding a clean spiral structure is diminished. The merger does not just scramble motion, it changes what the system can become afterward. So by the time the galaxies have passed through each other multiple times and finally settle, the outcome is not two damaged spirals still pretending to be spirals. It is a new object, a mixed population of stars from both parents, so intermingled you cannot tell which galaxy a given star originally belonged to. A system with a new centre of gravity, new orbital patterns, and a new visual identity in the sky. In the next part, we bring the camera back down to the scale that actually matters to life. If stars rarely collide and planets usually keep their orbits, what are the real risks of living through a galaxy merger? The answer is not impact, it is proximity, radiation, and the fragile outskirts of planetary systems. If you are looking for the part of this story where life actually gets nervous, it is not the moment galaxies overlap. It is not stars hitting the horn stars. It is the quiet secondary effects that only matter if you live on something fragile, like a planet with an atmosphere, oceans, and a history that can be erased. The good news is that planetary systems are stubborn. The gravitational bond between a star and its planets is far stronger than the slow tidal tug of a distant galaxy. Earth does not orbit the Milky Way. Earth orbits the Sun. The Milky Way is the background stage, and for most of this merger, that stage can rearrange itself without knocking the actors off their marks. But the stage does have one trick that can reach into the life of a planetary system. Not by grabbing the inner planets directly, but by shaking the loose material at the edges. Out beyond the known planets, far beyond the Kuiper belt, there is thought to be a vast reservoir of icy bodies surrounding the solar system. The Oort cloud. It is not a neat ring, it is more like a loose, spherical swarm. A distant halo of comets, billions of them, leftovers from the early solar system that never became planets. What makes the Oort cloud important is not its beauty, it is how weakly it is held. Those comets sit so far from the Sun that the Sun's gravity barely has a grip on them. The outer Oort cloud can extend to around a light year from the Sun, which is a distance so large it feels like it belongs to the galaxy rather than the solar system. Objects out there move slowly. They are delicately balanced. A tiny push can change everything. And during a galaxy merger, the definition of tiny changes. As the Milky Way and Andromeda interact, the density of stars in some regions increases. Not enough to make space crowded in a human sense, but enough to make close passes between stars more likely than they were before. A star passing within a few light years of the Sun would not do much to Earth directly, but it could disturb the Oort cloud. It could nudge comets into new trajectories, and some of those new trajectories point inward. That is the first real danger. A long era of increased comet delivery into the inner solar system. In calm times, comets from the Oort cloud occasionally drop in, like rare visitors from deep time. During the merger, that trickle could become a busier stream. Instead of a few significant comets over very long spans, you could see dozens or more across the same span. It is not a guarantee, it is not a steady rhythm, but the odds tilt, and comets are not harmless snowballs. A large impact can rewrite a planet's climate, collapse ecosystems, and trigger mass extinctions. It does not need to hit often to matter, it only needs to hit once at the wrong time. There is a second layer to that danger that feels almost unfair. A comet does not have to strike the planet directly to cause trouble. Impacts can throw dust and aerosols into the atmosphere, dim sunlight, disrupt photosynthesis, acidify oceans, and cascade through food webs. If life is clinging to a narrow band of habitability, a few unlucky impacts across a few million years can be enough to push it over the edge. So in this story, the galaxies do not kill worlds by smashing stars. They increase the number of lottery tickets in a game where the prize is catastrophe. The next risk comes from the bright side of the merger: star formation. When gas clouds compress and starbursts ignite, the galaxy produces more massive stars than usual. Massive stars are spectacular, but they are short-lived, and their deaths are violent. More massive stars means more supernovae. A supernova is dangerous only if it happens nearby. Space is still huge, and even in the starburst era, most supernovae go off far away. But the risk does not come from most. It comes from one that is close enough to matter. If a supernova occurs within a few dozen light years of a planet with life, it can strip away part of the atmosphere, or at least damage protective chemistry like an ozone layer, letting more ultraviolet radiation reach the surface. It can also bathe the planet in high-energy particles and radiation. Life might survive in oceans or underground, but surface ecosystems could take a brutal hit. During the merger, the overall rate of supernovae rises. That does not guarantee a nearby one. It simply increases the number of rolls. If you live through millions of years of elevated supernova activity, the probability of one happening in your dangerous radius goes up. There is also a subtle interaction between the two risks. More star formation creates more radiation and more turbulence in the interstellar medium. That turbulence can change where stars end up, and in rare cases, it can put a planetary system closer to active star-forming regions than it used to be. Most stars will never pass close enough to a massive star cluster to notice, but some will, so the hazard map of the galaxy becomes uneven. Some regions become harsher, others remain relatively calm. And that means survival is not only about how advanced you are or how tough your biosphere is, it is also about where you happen to be during the worst phases. There is one more risk that sounds dramatic and is actually rare, but it deserves a clear mention because it is the kind of thing people secretly imagine. A close stellar encounter. Even in a merger, direct star collisions are essentially negligible. But stars can pass close enough to each other for gravity to matter. If another star passes within roughly a light year of the Sun, the outer solar system could be disturbed. Wide orbit objects, distant comets, maybe even the paths of outer planets under extreme scenarios. If a star passes much closer, deep inside the region of the giant planets, then all bets start to weaken, and planetary orbits could be altered more severely. How likely is that? Still very low. Even during the densest phases, estimates put truly disruptive encounters as well under 1% for any given star. The galaxy is vast, and the merger lasts a long time, but the target zones for severe disruption are tiny compared to the total volume. So the honest picture is not a guaranteed apocalypse. It is a long period of increased risk. And now the final twist, or the one that makes the universe feel like a machine that never stops building even while it breaks things. The same mechanisms that create hazards also create opportunities. Comets do not only bring destruction, they also carry water and organic compounds. In the early history of the solar system, comets likely delivered some of the ingredients that helped make Earth wet and chemically interesting. During a merger, when comet trajectories are disturbed across millions of systems, impacts could seed worlds with water and organics that were previously scarce. The merger could increase the number of habitable candidates, even as it increases the number of extinction events. Supernovae are also double-edged. They can damage life, yes, but they also enrich the galaxy with heavy elements. The iron in your blood and the oxygen you breathe come from stellar processes and stellar deaths. Starbursts and their supernovae inject fresh material into the gas that forms the next generation of stars and planets. That can lead to more rocky planets, more complex chemistry, and more energy sources inside planets from radioactive elements. So the merger is not a simple villain. It is a filter. It increases the churn. It punishes fragility in unlucky places. It also expands possibility across the galaxy by creating new stars, new planets, and new chemical richness. If you are a civilization trying to survive this era, the strategy becomes clear. Do not treat the merger as a single event. Treat it as a long environmental shift. Track your neighborhood. Monitor nearby star-forming regions. Watch for supernova risks. Understand the trajectories of comets. And if you can move away from the most chaotic zones. Because the galaxies will not care whether anyone survives. But life and intelligence, if they exist, can care and can adapt. And while all of this is playing out on the scale of stars and worlds, there is another drama building at the centers of the galaxies, a drama that does not happen in the sky as visible fireworks, but in gravity itself. The supermassive black holes are on a collision course of their own. Far from the spiral arms, far from the calm regions where stars keep polite distances, the merger has a darker heartbeat. Each galaxy carries a supermassive black hole in its center, a mass so concentrated that the surrounding stars orbit as if chained to an invisible stake. The Milky Way's central black hole is Sagittarius' star, about 4 million times the mass of the Sun. Andromeda's central black hole is far larger, somewhere around 100 million to 200 million solar masses. Two anchors, two beasts, 2 points of gravity that do not care about beauty, only about binding. As the galaxies swing through their first close encounter, the black holes do not immediately collide. They are still separated by enormous distances, wrapped in their own dense stellar environments. But the merger changes the one thing black holes crave most. It changes the flow of gas. When galaxies interact, gas is stirred, shocked, compressed, and funneled inward. Orbits that used to keep gas in stable lanes become unstable. Clouds lose angular momentum. Material spirals toward the center like water finding a drain. And when gas falls toward a supermassive black hole, it does not simply vanish in silence. It heats up. It forms a swirling disk. It glows. This is how a quiet black hole becomes an active one. An active galactic nucleus is a region around a black hole wherein falling matter becomes so hot and so energetic that it can outshine billions of stars. The black hole itself still emits no light, but the gas around it can blaze. If the merger funnels enough material inward at the right time, the centers of the galaxies can flare into brilliant beacons, visible across the universe. From inside the galaxies, you might not see it as a sharp point of light because dust can hide the view, and because you are embedded in the system. But across many wavelengths of light, the event would be obvious. The cores would wake up. Now imagine two cores waking up in the same neighborhood during repeated close passages, while the entire stellar population is being jostled and the gas is being driven into storms. It would be one of the most energetic eras in the life of the combined system, not because the stars are crashing, but because gravity is rearranging fuel and feeding the darkest engines we know. As the merger continues, dynamical friction and gravitational interactions slowly bring the two central regions closer. Over hundreds of millions of years, the black holes begin to share the same deep gravitational well. Eventually, they form a binary system. Two supermassive black holes orbiting each other, each one dragging space and time into a slow tightening spiral. This is where the story becomes almost eerie in its quietness. The most violent energy release in the coming black hole merger will not be light. It will be gravitational waves. Gravitational waves are ripples in space-time produced when massive objects accelerate. They were predicted long ago, and in our era we have already detected them from mergers of smaller black holes, the kind formed when massive stars collapse. But a pair of supermassive black holes that radiates gravitational waves at much lower frequencies. The ripples are longer, slower, deeper. Detecting them requires different kinds of instruments. One of the future missions designed for this is the Laser Interferometer Space Antenna. a space-based observatory meant to listen for low-frequency gravitational waves. Civilizations far in the future, if any are still doing science with a pulse, might measure the slow drumbeat of the binary long before the final plunge. They would watch the orbit tighten over time as the system loses energy through gravitational radiation. At first, the black holes circle each other with wide separation. Then gradually the orbit shrinks, the period shortens. Millions of years of slow decay, then faster. The final moments happen quickly compared to the rest of the bodega. The black holes whirl around each other at a significant fraction of the speed of light, and then, in a sudden and clean event, they become one. The combined black hole would have a mass roughly equal to the sum of its parts minus a small portion radiated away as gravitational waves. That missing mass becomes pure wave energy, carried outward through the universe as a shiver in space-time. The total power released for a brief time is enormous, rivaling the combined starlight of galaxies. But again, it is not starlight. Without a gravitational wave detector, you would not see it. The universe would shake, and the sky could look perfectly normal. There is another twist after the merger, one that feels almost like a cosmic mischief. The gravitational waves are not always emitted perfectly symmetrically. If the masses and spins are arranged in just the wrong way, the newly formed black hole can receive a recoil kick. It is like a cannon firing in all directions except one, and the black hole moves in the opposite direction. The kick could be hundreds of kilometers per second, and in extreme scenarios possibly more. What happens then depends on how strong the kick is compared to the gravity of the new galaxy. In many cases, the black hole stays bound. It wanders. It oscillates through the central regions, slowly losing energy. Slowly settling back toward the deepest point of the gravitational well. Over millions of years, it returns to center, like a heavy object finding the bottom of a bowl. Could this wandering black hole be dangerous? In principle, yes. A supermassive black hole passing close to a star can tear it apart in a tidal disruption event, shredding it into a stream of hot gas that flares brightly as it falls inward. It is one of the most spectacular ways a star can die. But in practice, the volume of space is so vast and the black hole's path is still a narrow thread through that volume. The odds of it wandering anywhere near a specific star system like ours are fantastically small. The more realistic influence of the central black hole era is indirect. If the core becomes active, the radiation environment near the center can become harsher. Powerful outflows can push gas around, heating it, expelling it, changing the future of star formation. The core can become a furnace that helps shut down the very starburst that fed it. In the language of galaxies, feeding can also be a kind of self-control. Too much energy injected into the gas can prevent further collapse, leaving the final system with less cold fuel and fewer new stars. So the black holes do not just mark the finale, they help shape the aftermath. The merger is not simply two disks becoming one cloud of stars. It is also two gravitational centers becoming one, and that single center changes how the newborn galaxy settles into its long middle age. In the next phase of the story, we follow the slow mechanism that makes the entire dance converge. The way motion is drained from the orbit, the way repeated encounters become less like flybys and more like surrender. The galaxies do not merge because they decide to. They merge because gravity knows how to take energy away, one long step at a time. The galaxies do not merge because they touch. They merge because they cannot keep their speed. Every close passage steals a little of their ability to swing away again. Not with friction the way air slows a falling leaf, but with a gravitational kind of drag that is almost poetic in how it works. A massive object moving through a sea of smaller objects pulls on them, and those smaller objects pull back. The massive object leaves a wake in the distribution behind it, and that wake tugs on the mover like a hand on its shoulder. The mover slows. Its energy does not vanish. It spreads into many small motions, many small orbit changes, many small random kicks across the galaxy. This is dynamical friction, and it is one of the main reasons the dance converges. Imagine the dense core of the Milky Way ploughing through the outskirts of Andromeda during a pass. Stars and dark matter in that region are disturbed. They are pulled into new trajectories. They clump briefly in patterns that lag behind the moving core. Those patterns become the wake. The wake becomes the pull. The pull becomes the slowdown, then reverse it. Andromeda's core does the same as it moves through the Milky Way's sea of matter. Both galaxies are breaking each other by reshaping each other. And because the breaking comes from gravity itself, it does not require contact. It does not require gas. It works even if the galaxies were made only of stars and dark matter. Gas makes the show brighter, but gravity is the accountant balancing the books. So after the first major encounter, the galaxies separate again, but not as far as they would have if nothing had changed. The second approach happens sooner. The next passage is tighter. The tidal distortions become stronger. The star formation surges again as gas is shocked and compressed in new ways. The spiral arms, already wounded, become harder to recognize. The disks become thicker and more warped. The galaxies look less like spirals and more like two broken storms colliding again and again. This stage of the merger is where the word chaotic finally feels appropriate. But even chaos has structure. The repeated passes create waves, ripples, shells and streams in the stellar distribution that can persist for billions of years. In a future sky, an observer might see faint arcs and overdensities that look like scars, echoes of earlier passages still moving through the system. From far away, the merger looks like slow-motion water. Two drops approaching, touching, stretching, separating, then returning, each time mixing more thoroughly, each time losing the clean boundaries that once made them distinct. By the third pass, the idea of the Milky Way and the idea of Andromeda are mostly labels of history. The stars are already interleaving. The gas is already mixing. The dark matter halos have long since overlapped and blended into one larger gravitational environment. And the deeper the mixing goes, the more the outcome becomes inevitable. Not because the galaxies are aimed like darts, but because their gravitational relationship has crossed a threshold. They are no longer two separate systems on two separate paths. They are one evolving system trying to settle into a stable shape. This is also when the fates of smaller galaxies become more precarious. Our cosmic neighborhood is not just two big spirals. The local group includes dozens of smaller galaxies, many of them faint dwarfs orbiting the two giants. Over long time, those smaller systems feel the changing gravity like a shifting tide. Some will have their orbits disturbed, some will be pulled inward, some will be stretched into streams, their stars becoming part of the growing merged halo. One of the more interesting neighbours is the Triangulum Galaxy, a smaller spiral that is gravitationally associated with the Andromeda system. Depending on the exact history of interactions, it may merge with Andromeda before the main Milky Way encounter, or it may be drawn into the combined system during or after the big merger. Either way, the story of Milky Way plus Andromeda is likely also a story of a neighbourhood gradually consolidating, gravity gathering scattered islands into one larger continent of stars. Meanwhile, closer to home, the Milky Way's own satellite galaxies continue their slow surrender. Long before Andromeda becomes enormous in the sky, some companions may already have been absorbed, their gas stripped, their stars smeared into streams around the Milky Way. By the time the big merger reaches its later passages, the two giants are not pristine spirals meeting for the first time. They are already layered with the remnants of smaller meals. So each pass does three things at once. It rearranges orbits, pushing the system toward a rounder, thicker, less ordered shape. It triggers new waves of star formation and later, waves of supernova activity as gas repeatedly collides and compresses. And it blends histories, folding satellite galaxies and stellar streams into a single shared structure. Eventually, there is a final phase where the galaxies stop separating in a meaningful way. Their cores sink toward a common center. The last wide swing is over. The remaining motion is less like two objects orbiting and more like one object settling. The central regions spiral inward through the sea of stars and dark matter, losing energy, tightening and finally becoming one combined core. By this point, the sky from inside the system would look nothing like the Milky Way, you know. There would be no clean disk, no confident spiral arms. The distribution of light would be more three-dimensional, more everywhere. It would feel like living inside a giant, slowly calming ember cloud. And as the system settles, another change becomes clearer. The merger burns through fuel. Starbursts consume cold gas. Supernova feedback heats and stirs what remains. Outflows can push some gas outward. The final galaxy is often left with far less cold material to form new stars than either parent had before the encounter. Which means the aftermath is not just a new shape, it is a new era. A brighter chaos that gradually cools into a quieter, older system. In the next part, we step into the invisible architecture that makes all of this possible. The dark matter halo. The massive, unseen structure that merges first, guides the dance, and ultimately holds the newborn galaxy together long after the last tidal tail fades. If you could strip away every star, every planet, every glowing cloud of gas, and leave only the gravity behind, the merger would still happen. That sentence feels wrong because we are trained to trust what we can see. But in a galaxy, what you see is not most of what there is. The Milky Way is wrapped in something enormous and invisible, a vast halo of dark matter extending far beyond the bright disk you picture when you hear the word galaxy. Andromeda has its own halo too, larger and heavier. These halos are not small accessories. They are the main gravitational structures of the galaxies. The stars are passengers riding inside a much larger, darker ship. We know this because galaxies rotate too fast to be held together by their visible matter alone. If you add up the mass of the stars and gas you can see, the outer parts of spiral galaxies should be moving so quickly that they fly apart. They do not, they stay bound. Something unseen adds extra gravity, holding the whole system together like an invisible scaffold. We also see the same invisible mass revealed in other ways, like the way gravity bends light from objects behind it, and the way entire clusters of galaxies remain bound when the visible mass is nowhere near enough. Dark matter is that extra mass. It does not glow, it does not absorb light, it does not reflect light. As far as we can tell, it barely interacts with normal matter except through gravity. It is the ultimate quiet presence everywhere, shaping everything while refusing to show its face. Now here is the crucial part for our story. When the Milky Way and Andromeda approach each other, their dark matter halos meet first. Long before the visible disks overlap, long before you could point to a star from Andromeda and say it is inside the Milky Way's territory, the halos have already interpenetrated. They are so large that the merger begins in the dark, with invisible material passing through invisible material, gravity blending into gravity. And unlike gas, dark matter does not crash. Gas collides, compresses, heats, and radiates. Dark matter does none of that. It behaves more like a swarm of tiny particles that can pass through each other almost without friction. Two halos overlap, and their contents simply mix, slowly, steadily, guided by gravity alone. This is why the merger is both dramatic and strangely smooth. The visible galaxies look like they are being torn apart, starbursts flaring, tidal tails stretching into space. But the underlying dark matter merger is more like two fog banks sliding into each other. Quiet, patient, relentless. Yet that quiet process does most of the work. The gravitational pull that draws the Milky Way and Andromeda together is dominated by their halos. The stars contribute, the gas contributes, but the bulk of the mass is dark matter, on the order of about 85% of all the matter in the universe. And in galaxies, it often outweighs everything you can see by several times. The visible parts are like foam on top of a deep ocean of gravity. So when astronomers simulate the coming collision, they do not just throw two disks of stars at each other and watch. They build halos. They give those halos shapes, concentrations, and internal motion. They embed the visible galaxy inside. Then they let gravity run forward and watch what happens. Change the halo and you change the movie. A more concentrated halo tends to create stronger tidal forces, a tighter grip, and a more violent reshaping of the disks. A more extended halo can produce a gentler encounter with different tidal structures and different timing. The halo affects how quickly the galaxies lose orbital energy. It influences how the cores sink toward each other. It even affects where tidal tails form and how long they remain visible. This means that the Milky Way-Andromeda merger is not only a spectacle, it is also a dark matter experiment on a cosmic scale. Because the shapes and motions we will observe as the approach continues, let us infer the invisible mass distribution guiding them. We cannot see dark matter directly, but gravity turns it into a shadow you can measure. The way stars stream outward, the way the outskirts warp, the way satellite galaxies move, the way the whole local group dances. All of it contains information about the unseen structure underneath. There is also a philosophical discomfort here, and it is worth feeling for a second. We live inside a galaxy whose true shape is mostly invisible to our eyes. Our home is embedded in something we cannot touch or detect with our senses. Dark matter passes through Earth, through you, through everything, and you do not notice. It is the most dominant material component of galaxies, and it behaves like a ghost, and yet it is the reason the Milky Way exists in the first place. In the early universe, dark matter clumped first, forming gravitational wells. Normal matter fell into those wells, cooled, formed disks, and ignited stars. The bright cosmos you love is built on an invisible framework. The Milky Way is a visible ornament hanging on a dark skeleton. So when you ask what happens when Andromeda hits the Milky Way, you are really asking what happens when two enormous dark structures overlap and merge, dragging their luminous contents into a new configuration. This also helps explain why the merger is not a simple two-body problem. The local group is full of smaller gravitational actors. Dwarf galaxies, streams of stars, and other satellites orbit within the combined gravitational field. Their paths are influenced by the halos too. Some satellites will be captured, some will be pulled into new orbits, some will be torn apart and absorbed. The dark matter merger changes the gravitational landscape for everything nearby, not just the two main galaxies. And by the end, when the last major passage is over and the system settles, the newborn galaxy will sit inside a new, larger halo. A combined dark matter structure holding a combined luminous structure. The visible galaxy might look like an elliptical swarm of stars, but the real binding agent will still be the invisible mass around it, extending far beyond the last stars you can see. Which brings us to the long future. Because the merger is not the end of the story, it is a turning point. After the galaxies blend and the starbursts fade, the new system begins a slower drift toward quiet. Star formation drops as gas is used up or heated. The brightest young stars die out. The galaxy becomes older, redder, calmer, and in the far distance the rest of the universe keeps expanding, accelerating away, carrying other galaxies beyond reach. In the next part, we follow that future past the spectacle. What Milky becomes, how its sky would look, and why the merger might also mark the beginning of a lonelier universe. After enough passages, enough stretching, enough starbursts, enough slow theft of motion, the system finally stops pretending it is two galaxies. The cores sink, the last wide swing ends, the remnants settle into a single blended structure that no longer has the clean geometry of a spiral disk. No crisp arms, no tidy plane, just a thick, rounded swarm of stars moving in many directions, held together by the combined gravity of everything that survived the dance. People sometimes nickname this future galaxy Milkomeda. The name is playful, but the thing itself is real. A new galaxy made from the Milky Way and Andromeda so thoroughly mixed that the old boundaries become meaningless. Stars from both parents share the same gravitational home, orbiting a common center in patterns that look more like a stirred cloud than a spinning record. And if you were somewhere inside it, the sky would feel unfamiliar in a way that is hard to describe from our current perspective. Right now, our view is shaped by living inside a disk. We see the Milky Way as a bright band because we are embedded in a flattened distribution of stars. In Milkomeda, that band disappears, not because the stars are gone, but because the geometry changes. Instead of a thin plane, stars would surround you more evenly. The night sky would look more like a luminous dome, with density gradients depending on where you are. If you're closer to the center, the sky could be crowded with stars, more of them bright to the naked eye, with fewer dark gaps between. The background would feel richer, almost granular, as if the universe has turned up the brightness knob. If you're far out in the halo, the sky would be darker, and the brightest feature might be a distant glow from the central regions, a pale core that never fully sets. Either way, the signature of a spiral galaxy is gone. The galaxy has become something older in spirit, more settled, more spheroid than disk. And that change also reshapes the future of star formation. Because a merger is a bonfire for cold gas. During the chaotic era, gas is driven into bursts of starbirth, then battered by radiation and supernovae, heated, stirred, and in some cases pushed outward. Some gas is consumed in forming new stars. some becomes too hot to collapse again, some can be expelled in winds or fountains. When the dust finally clears, the newborn galaxy is often left with less of the cold, dense gas needed to keep forming stars at a high rate. That means Milky gradually quiets down. The brilliant short-lived blue stars that made the starburst sky look electric die out quickly on cosmic time. Supernova rates fall as the burst population ages. The galaxy's light shifts toward older, longer-lived stars, the kind that glow more softly and more steadily. Over billions of years, the galaxy becomes calmer, redder, and less willing to make new suns. This is not a tragedy. It is a life cycle. Galaxies are not static monuments. They are living ecosystems of matter and motion. They grow by merging. They shine by forming stars. And they fade as they run out of easy fuel. Milky is not the end of that cycle, but it is a transition into a quieter chapter. And now the story zooms out again, because while the local group is busy consolidating, the rest of the universe is doing something even stranger. The universe is expanding, and that expansion is accelerating, driven by something we call dark energy. Dark energy is not well understood, but the effect is clear. Over huge scales, space itself stretches in a way that carries distant galaxies away from each other. The farther a galaxy is, the faster it recedes, not because it is flying through space like a rocket, but because the space between us is growing. Inside gravitationally bound regions like the local group, gravity wins. That is why the Milky Way and Andromeda can merge at all. But outside that bound neighborhood, expansion wins, and over deep time it wins harder. So as Milky settles, the wider universe begins to thin out from our perspective. Galaxies that are not gravitationally bound to our region will drift farther away, their light stretched to longer wavelengths, their brightness dimming with distance. Eventually, many of them slip beyond a cosmic horizon, a distance where their light can no longer reach us in any meaningful way, because space expands too quickly in between. This creates one of the most haunting predictions in cosmology. Far in the future, an astronomer living inside Milky could look outward and see a much emptier universe than we see today. In our era, we can detect galaxies billions of light years away. We can map large-scale structure. We can observe the leftover glow from the early universe, the cosmic microwave background. But that is a privilege of timing. It is not guaranteed forever. In a far future era, Milky may appear almost alone, surrounded by darkness, with only a few nearby remnants still visible, possibly some faint satellite galaxies that remained bound. The grand cosmic web that we can study today would be gone from view, not gone in reality, but carried out of reach by the stretching of space. That means future civilizations could end up with a narrower view of reality, even if they are smarter than we are. Their universe would look smaller, not because it is smaller, but because the evidence has slipped beyond their horizon. They might have to reconstruct the true cosmic history from fossils of physics rather than from direct observation. They would live inside a galaxy that remembers the merger, but they would not easily see the broader universe that once surrounded it. And there is one more quiet shift layered on top of all this. Milky itself will keep aging. Stars like the Sun will evolve off their stable phase, swell, shed their outer layers, and leave behind remnants like white dwarfs. More massive stars will become neutron stars or black holes. Over long stretches, the galaxy will become increasingly dominated by stellar remnants and long-lived small stars. The bright, youthful look of the starburst era will feel like ancient history. So the merger gives us two futures at once, a future where our local environment becomes one new galaxy, reshaped and quieter, and a future where the wider universe slowly disappears from view, leaving that new galaxy as one of the last bright islands in a growing sea of darkness. This is why the Andromeda merger is not just a local event. It is a chapter in a larger cosmic story. A story about gravity building structure while expansion erases the view. A story about how the universe can be both wildly eventful and eerily indifferent, depending on the scale you choose. In the final part, we return to the most human question hiding underneath all of this. What does it mean to live in a universe that changes this way, and why are we in a rare moment where we can see the cosmic stage before it starts to fade? Somewhere deep inside this story is a strange emotional trap. You can spend an hour imagining the Milky Way and Andromeda twisting together, gas igniting into starbursts, black holes spiraling into one, and a brand new galaxy rising out of the chaos. And then you remember the timeline. 4 billion years, give or take hundreds of millions. A span so large that almost everything you know, almost everything you care about, almost everything your species has ever built, becomes a brief flicker on the opening credits. So why does this matter? Not because it threatens you. It does not in any practical sense. By the time Andromeda becomes a dominating presence in the sky, Earth will already be profoundly changed by a much closer influence. The Sun itself. Stars like the Sun brighten slowly as they age. The increase is gentle per year, but relentless over long time. Within about 1 billion years, Earth is expected to cross a threshold where its climate becomes unstable for liquid water on the surface. Oceans begin to evaporate. Water vapor is a greenhouse gas, so warming accelerates. The planet can enter a runaway greenhouse state, becoming more like Venus than the Earth you know. That happens long before the galaxies truly merge. By the time Andromeda is close enough to redraw the sky, Earth is likely already uninhabitable at the surface. Not because of the merger, because the Sun has been quietly turning up its power for billions of years. The universe does not need a galaxy collision to end a biosphere. One aging star is enough. So if any descendants of Earth are around to witness the merger, they will not be standing in forests looking up. They will be elsewhere, perhaps on habitats in the outer solar system, perhaps among the moons of the gas giants, perhaps in engineered worlds in deep space, perhaps far beyond the solar system entirely, or perhaps nothing remains. Extinction is always an option in the universe's menu of outcomes, and yet even if Earth is gone as a home, the merger still raises a more precise question. What happens to the solar system as a physical system during the collision? The honest answer is that in most scenarios, not much. The Sun continues to hold its planets. The planets continue to orbit. The merger rearranges the Sun's path through the galaxy, but it does so gradually, like a tide changing a ship's route over long time, not like a wave flipping it instantly. There is a small chance of a close encounter with another star during the densest phases. Such an encounter could disturb the outer solar system. It could stir the Oort cloud, increase comet showers, maybe alter the orbits of distant bodies. Very rarely a truly close pass could do more dramatic things, but those events are not the typical outcome. The galaxy is still vast, and even in a merger, stars usually keep their distance. Meanwhile, the Sun's own destiny continues on schedule. Around the time the merger gets serious, the Sun is approaching the later stages of its stable life. Within another 1 billion years or so after the merger era begins, the Sun will start to transform into a red giant. Its core will contract, its outer layers will expand enormously, and the inner solar system will be roasted. Mercury and Venus are almost certainly doomed. Earth is at risk of being swallowed as well, or if not swallowed, heated until its surface melts, and the last physical traces of oceans and atmosphere are erased. That fate is not caused by Andromeda. It is written in the Sun's mass. Stars of this size age in predictable ways. The merger does not change the nuclear physics in the Sun's core. It only changes the galactic neighborhood the Sun happens to occupy while it grows old. So if you are trying to locate the real killer of Earth in this story, it is not 1 trillion stars falling toward us. It is one star slowly brightening in the center of our own days, which makes the merger feel less like a disaster movie and more like a cosmic documentary about context. Your planet is not the main character. It is a footnote in a much larger dynamic system. The galaxy does not care that life happened to bloom here. The merger will proceed according to gravity whether anyone watches or not. And that is exactly what makes this story powerful, because you're watching it now. You're alive at a time when Andromeda is still a faint smudge, when the Milky Way is still a spiral disk, when you can still see other galaxies across the sky, when the cosmic microwave background is still detectable, when the universe is young enough and bright enough that its history is still readable in the light. This is not a permanent situation. In the far future, after Milky forms and the universe stretches everything else away, an astronomer might look outward and see only darkness beyond their own island of stars. They might never discover that billions of other galaxies exist beyond their horizon. Their universe would appear smaller, Not because it is smaller, but because the evidence has slipped away. So we live in a rare observational window, a moment where the universe is both old enough to have built complexity and still open enough to be seen. That is the deeper lesson of the Andromeda merger. Not that we are doomed, but that everything is temporary, even on scales that feel eternal. Galaxies merge, stars evolve, habitable zones shift, cosmic horizons close. The universe changes its rules of accessibility over time, not by changing physics, but by changing what physics allows you to observe. And somehow inside that impermanence, there is a kind of meaning. We are made of atoms forged in stars. The oxygen in your lungs, the iron in your blood, the carbon in your thoughts, all of it was built in ancient stellar furnaces and scattered by explosions. The merger you fear is also the same process that built the galaxies in the first place. Most large galaxies are not pristine creations. They are the result of many mergers over cosmic history, countless smaller systems swallowed and blended into one. The Milky Way has already been doing this for billions of years. Andromeda has too. The coming merger is just the biggest local chapter in an ongoing habit of gravity. So when you picture the final shape of Milkomeda, you are not picturing an end. You are picturing a transformation, a new galaxy, older and rounder, calmer and dimmer, still holding trillions of stars, still carrying the remnants of countless histories, still orbiting within its dark matter halo like a jewel embedded in invisible stone. And if any minds exist then, looking up at a sky that no longer has a Milky Way band, they might still feel the same strange mix of smallness and connection that you feel now. The universe is huge. It does not revolve around anyone, but it does produce beings capable of understanding it, beings who can see a collision 4 billion years away and turn it into a story. That might be the rarest thing of all.